Hey everybody, good morning. How are you? So good to see you. Happy Sunday. Hope that you're doing well out there in your part of the world. Let me adjust my camera. I had to make some last minute adjustments to my camera as I was getting ready. I think this will be good here. All right. How's everybody doing? Thank you so much for joining me again for the Sunday series where we are going to continue talking about neural networks. I think that we are now in week 4 of neural networks. So looking forward to seeing where the discussion heads this time. We've had some really good discussion the last couple of sessions, really good participation. Thank you so much for that. So let's see where we end up this time around in terms of the different pieces that we can keep on building from our previous times. Um, we've had some success in doing some of the reviews. We've had some success in the code that we've been getting from AI. And we've also had some success in fine-tuning these models as they go along. So today we're going to kind of start to put all of that together and also start to put some more theory behind it, because I hope that some of you are seeing that the code behind neural networks is probably not as intimidating as you think it is, but it's really more about a thought process and how you approach the general problem of creating and managing and designing the neural networks, right? So I think that we're in for some good discussion around that, and just kind of see where we end up. So I'm here for as long as you need me. Maybe for the next hour, 2 hours. Who knows? We seem to kind of been skipping around, but we have gone 2 hours a couple of times. But we'll see where we end up today. I have a couple of things in mind that I want to get across, but always open to your feedback and all the questions, see where it takes us. Speaking of which, feel free to go ahead and add to my chat. You can see that my chat here will start to fill up as more people start coming in. So feel free to come in, say hello, let us know how you're doing, and we'll start the class as soon as we get a couple of people here. You're going to have to bear with me because I was thinking about this as I was putting the materials together. I know that there's a lot of concepts that I still want to get across, but it's not always easy to get those concepts across in a way that makes sense, like from a building blocks perspective, because you're not always going to use every single thing in neural networks. Some of these things you're just going to kind of use once and never touch again. Others you're going to use on a regular basis, depending on how you go about with your neural networks implementation, depending on the type of data that you're working on, right? So we're going to kind of feel our way along here in the next 2 weeks, maybe. That'll go into one more week. I'm not 100% sure. But we're going to see how we get along. We're going to stay optimistic, stay positive, but it's going to be learning nonetheless, right? And hopefully I'm giving you enough information to explore it on your own, to be a little more confident on your own. And, see where we end up there. Okay, so let me check my chat real quick. Starting off with our good friend from Morocco, Osama. Osama, how are you, my friend? Hi, sir. Good to see you. I hope everything is going well. Everything is going very well. Thank you, Osama. Yeah, it's been an active week over here. I've been taking care of a lot of things on my end, but otherwise, it's been a good week. Hope the same for you. Let us know how you're doing out there in your part of the world. I'm assuming that it's getting a little bit warmer out there in Northern Africa, so let me know how you're doing. Andre over on Twitch. Andre, I think it's your first time, so welcome. Always good to see Twitch people on here. Andre says, is pathfinding algorithm stuff still somewhat matched up with neural network stuff, or is that more of a different branch? Good question. Andre, I would love to hear your definition of a pathfinding algorithm. I have a feeling I know what you're talking about, but let me just to kind of calibrate our understanding with each other. Let me know what you mean by the pathfinding algorithm. I'm assuming you're talking about like like the contests where they have the mazes and you design a car or a mouse, I think is the intention, to run through the mazes, you know, with that type of pathfinding. Let me know if that's what you mean. But yeah, thanks for being here, Andre. Is it Bach? Let me know if I'm pronouncing that right. I think it's Bach. Bach says, hi, Mr. Dennis. Hey, Bach, nice to see you. Bach, I think it's your first time. I don't remember your name from before. Let us know how you're doing, but welcome. If you feel like sharing what part of the world you're in, we'd love to hear it. Thanks for being here. Our good friend Denelson. How are you, my friend? Good morning, Sir Dennis. Denelson from LA. Ready to start learning. How has everyone's week been? Hey, Denelson, nice to see you. Glad to see that you're in LA. My parents are out in LA right now, as a matter of fact. So everyone's week, I think, has been okay. How has your week been, Denelson? My week has been taking care of a lot of different personal things on my end. Different things I've been trying to address, but otherwise things are going well. So thanks, Denelson. Thanks for asking. Manoj, our good friend Manoj says, hello, Sir Dennis and everyone. Manoj from Bangalore, India. How are you, Manoj? Hope you're doing well out there in Bangalore. Assuming that it's very warm out there, so hope you're staying cool out there. All right, so Andre asked about some algorithms. So for additional information, I thought the definition was in the name, but to a point, yes. I just wasn't sure if that leaned more into neural network building or if that was considered a different section of that. Well, you still haven't told us your definition. So let us know, Andre. Okay, if I also see people over on Instagram. If you're on Instagram, feel free to say hello. Let us know how you're doing. Feel free to stay on Instagram, or you can join us over on YouTube for a wider screen view. But if you are over on Instagram, don't be shy. Feel free to say hello. Just let us know how you're doing. And let me actually fix one more thing on my end to make sure that I'm going to get all the Instagram chats. That's always a challenge with the software I use. All right, guys. So if there's nobody else that wants to introduce themselves, we can go ahead and get started. I love the lightning reviews that we've been doing. I think that sparks up a lot of conversation, and I have a couple of those that I want to do today. So let me know if anybody else wants to introduce themselves. Oh, Bach says, not my first time. I have followed you since last year. Bought your books. I'm that DS major student. You may have forgotten me, Mr. Dennis. Love from Vietnam. Bach from Vietnam. Bach, I apologize, but I think my memory might be failing me there. So thanks for being here. Good to see you. And yes, the pronunciation is flawless. Thanks, Mr. Dan. I appreciate that, Bach. So Bach, I always love hearing about people coming back. You know, guys, I got to tell you something. Sometimes that bothers me a little because people will DM me like in private and they'll say like, oh, like they're embarrassed, like they're shy that they missed a couple of Sundays or they missed some of my live streams and they're like embarrassed to come back. Definitely don't do that. So Bach, I love the fact that you came back. Don't be shy. I love that you're jumping right back into it. Thank you so much for that. Always good to see people joining. So thanks for being here. Parth, welcome. Parth says, hello, sir. I'm new to this channel. I found it while surfing through some neural networking videos. I am a budding game developer and I have some doubts, like how is neural networks used in games? Okay. So guys, that seems like a pretty good review question to start off. In the chat, let me know, what are some ideas where a video game could be using neural networks? Spoiler alert, there's a lot of them, right? But if you guys want to just kind of start the brain juices flowing, let's help out our new friend Parth. How could a game be using neural networks? Let me know. Is it Khalid? I think it's Khalid. Khalid over on Instagram. Welcome on Instagram. Khalid says, hello, a big fan or more of a student, actually. I'm from Sudan. I hope you're good. I hope you're good. I'm working on a project recently using neural networks for detection of breast cancer, malignant and benign. Anything on the topic? Okay, cool. So Khalid, welcome. Love having you here. You're welcome to stay on Instagram or join us over on YouTube for the wider screen view. So I'm going to assume that you're working with image data, right? So Khalid, we're going to talk a little bit about image data today, just a little bit. But just to get your thoughts going, Khalid and everybody else in the chat, what makes image data special? When you think about image data, but more importantly, how you have to explain it to a neural network, what makes it special? What makes it special, guys? Denelson says, week has been hectic this week. We had some team members laid off at work. I was fortunate enough to not be affected, but we are down to half our force. Wow. Sorry to hear about your coworkers, Denelson. You know, that's kind of a weird position to be in, right? Because I don't want to say congrats, Denelson, because I don't know if that's something to celebrate. I mean, obviously, I'm happy that you're not unemployed. I'm sure you are too. But you kind of don't want to celebrate other people being laid off, right? And unfortunately, you know, Denelson, that is something that's increasingly happening across the US and across the globe, right? So happy to hear that you're still employed. But obviously, you know, that does probably create some more work on your end, more responsibilities on your end, which can be a blessing. I am coaching some people who are in that situation. I'm coaching some people who are looking for work. I'm coaching people who have recently found work. It's a dynamic landscape for jobs right now. So Denelson, glad to hear that you were able to avoid being laid off. And if there's a way we can support you, let us know, okay? Okay, so Parth, coming back to the question of how would you use neural networks in game development? Well, I guess for NPC behaviors, I'm not exactly sure. Yeah, NPC behaviors could definitely be a use of neural networks. Really any type of activity that you either want to, you know, mimic or randomize or different things along those lines, right? Something where you kind of want there to be like, I guess for the lack of a better word, some randomization, or really kind of autonomy, right? Because, you know, I keep on telling you guys how for me, learning neural networks was really kind of like where I really understood the power of data science, right? And that's part of it, right? That when you start working with neural networks, you really kind of start seeing the autonomy of how you can use algorithms for like automated decisions, right? So really anything in a game that would require autonomy is probably a pretty good candidate for a neural network, right? Now, having said that, you know what? Let's put a pin in this. I'm gonna hold my thought until we do the lightning round review. Yeah, because I want to tie that back into something. Parth, I'm gonna tie in the answer to one of the lightning review questions. Okay. Okay, so Bach says, now I'm a second year, currently learning discrete math and beginner neural networks. I really look forward to your insights. Cool. Yeah, you come to the right place. Hopefully I'll give you a leg up on some of the stuff that you may already be learning in your classes, Bach. So thanks for being here. All right, guys. So last call for introductions. Otherwise, I'm going to bring up my classroom view and we're going to get started and we're going to jump right in, guys. We're going to jump right in to another lightning round review. So last call for introductions, and then we're going to go ahead and get started. Let me double check all my chat windows. All right, guys. All right, so let me bring up my classroom view. So neural networks week 5. Wow, guys, we've gone 5 videos in this series. Great job for staying in there with me. Okay, so lightning round review is up on the screen. Only 3 questions this time. And just as before, you don't have to answer all 3. You don't have to answer in order. Just give me your thoughts. Just tell me what question you're going after and put your answer in the chat. What is the effect of adding more epochs to our training cycle? What is the effect of adding more nodes to our layers? And what is a learning rate? Just pick one or pick all 3, whatever you want. And if somebody puts an answer and you're too shy, you can always just say, I agree with so-and-so, or I agree with that answer. But give you guys a few seconds here to think about it. Give me some answers to what is the effect of adding more epochs to our training cycle? What is the effect of adding more nodes to our layers? And what is a learning rate? What do you guys think? Some of these should be easier than others, but let me know. Parth says, for the first one, I guess the accuracy improves. Is that true? Is that true, guys? Let me know in the chat. You can just say, hey, I agree with Parth, or you can give up your own answer, right? But let's see if there's any other answers out there or people that want to attend try to attempt other questions. But for what is the effect of adding more epochs to our training cycle, Parth says, I'm guessing the accuracy improves. That's a perfectly reasonable answer, right? Let me know what you guys think in the chat here. Khalid says, more epochs means more chance to learn patterns. Yeah. I mean, Parth and Khalid, you're giving up very similar answers, right? And yeah, that is the case, right? The longer you have epochs, or excuse me, the more epochs you have, the more there's an opportunity for your algorithm to train, right? Does that guarantee you reaching a good accuracy level or improving your algorithm? What do you guys think about that? Is it basically gonna improve your accuracy in all scenarios? Parth says, I mean, training accuracy keeps going up, but validation test accuracy might drop, so that's why I'm not 100% sure. Okay. Osama for saying, overfitting, the model starts to memorize the training data rather than generalizing it. Okay, so Osama's presenting a little bit of a contrasting view, maybe? Or maybe not a contrasting view, but he's presenting the other side of the coin, right? So yeah, overfitting could also be part of epochs, right? But what do you guys think? Are you guaranteed to improve? More epochs equals more better? What do you guys think? Or what do you guys think about the other questions? Everybody's answered question 1 so far, but what about 2 or 3? What about learning rate? We kind of learned that last week, right? We came up with some very reasonable explanations for learning rate, and we used learning rate, right? Learning rate benefited us a lot last week. What do you guys think? Give you guys another few seconds here. Michael, our good friend Michael from Nigeria. How are you, Michael? So good to see you. For number 3, what is a learning rate? Michael says, how fast or slow the network learns from the mistakes it makes during training in order to improve its accuracy. Michael also says, happy Sunday, Sir Dennis, and everyone. Happy Sunday to you too, Michael. Excuse me. So how fast or slow The network learns from the mistakes it makes during training in order to improve its accuracy. Okay. That sounds like a perfectly reasonable explanation, right? So, Michael, um, so learning rate, if that's the speed at which it learns, like your definition says, right? How fast or slow? So that means a higher learning rate is better? Is that what I'm understanding? So more learning rate, more better, right? Let me know, Michael. Art says the learning rate is the pace at which your model learns. Too fast and it goes haywire, too slow and it wastes time. The magic is in finding the right balance. At least that's what I learned in classes. Okay. Um Help me understand what you mean by pace. Because remember, this is all, all data science or neural networks in particular, it's all just a mathematical representation, right? So what do you mean by pace when it comes to math? Vaibhav, welcome back. How are you, my friend? For question one, Vaibhav says, but wouldn't it lead to overtraining at some point? Might need some restriction on epochs. Maybe. Vaibhav, I don't know if you've attended our previous sessions in this neural network series, but is that what we saw in our experiments? What do you guys think? If you guys have been here during our previous sessions, did we see that in our previous code runs? Did we see that we needed to restrict epochs because of overtraining? Khalid says the learning rates control the weights that updates during the training. Low rate makes the training slow. Okay. Okay, well, slow sounds bad. So more learning rate, more better. Is that what you're telling me? Um, I think it's Naaman, right? Or yeah, I think it's Naaman. Naaman says over on Instagram says learning rate is used to determine by a factor of what our gradients or weights will be changed per epoch. Okay. Okay. Um Parth says, when I said pace, I meant how big or small the changes are in the model's weights during the training after each learning step, or simply the iteration. Okay. Okay, cool. Um, so Naren says, hi, I'm Naren. I'm thinking out loud. How does training loss and validation loss relate to those questions? Sorry, this is not an answer. Well, it can be in a lot of ways, right? Fabricio says, hi, Dennis. Hey, Fabricio, nice to see you again. Hope you're doing well out there, my friend. Let us know how you're doing. Vibob says, hi, Dennis. This is my first neural network class, but yes, I used to attend your ISLP classes last year. Yeah, I remember Vibob. How are you? Good to see you again. Yeah, if you guys want to know what he's referring to, that's the Introduction to Statistical Learning book. That was my first full series that I did. That was a lot of fun, so you can definitely find that on my YouTube channel if you'd like to see that. I have a whole playlist for that one. So Bach says, my book said that learning rate is a hyperparameter that controls how much the model's weights are adjusted in response to the estimated error. During training, please correct me. Yeah, no, I'm generally on board with that definition, but you got to have a sense for the scale, right? Like, is it more, the higher number is better or a lower number is better? Right? Michael says too high or too low can cause problems, so it's important to pick a good learning rate that help in training and efficiently, accurately. Okay. All right, Michael, that's pretty reasonable. Over on Instagram, I'm sorry that your chat didn't come through for some reason, but I think it's Luann or Luana says it depends on the batch size and many other hyperparameters. Okay. Care to explain what a hyperparameter is? Because you're hitting on some of the topics we're going to talk about today. So Naaman says more means our weight will jump faster. It can lead to problems like jumping gradients. If it's too small, we can get vanishing gradients. So we need to select an appropriate learning rate. Will that lead to vanishing gradients? You had me all the way up to too small can get vanishing gradients. I don't know. I don't know if I'm on board with that part of it. What do you guys think? Does learning rate contribute? Does a lower learning rate contribute to vanishing gradients? I don't know. I'm going to say no. Change my mind. Let me know, guys. More epochs, yes, make it better a learning pattern, but at a point it will be overfitting to use validation loss. Okay. When data is limited, more epochs help the model learn robust features by revisiting the sample repeatedly. Okay. Yep. I'm sorry, I don't know. Your name is showing up as Arabic in my chat, so if you want to give me a name to use, I'd appreciate it. So they're saying lower. I'm assuming they mean the learning rate lower. Fabricio says lower learning rate is better. It helps move the gradient step by step instead of jumping fast and goes in the wrong direction and never converges, or worse, stuck in a local minimum. Okay. Yeah, so let's talk about that. I'm going to go ahead and remind you guys that not every neural network results in a positive result, right? Not every neural network converges. So more epochs is not always more better. You know, as I was asking in some of my earlier replies, right? Just because you add more epochs doesn't mean that you're going to get a better result. And I'm stopping to say that now because Fabrizio and at least one other answer was talking about the local minimas, right? And your training can get stuck in local minimas that epochs won't help you. They won't help you at all. So be careful about equating more epochs to improvement. That's not always the case. So we won't be learning it this week, we'll probably be learning it next week, is that within neural networks, there's the concept of early stopping. Why do you use early stopping? Exactly for reasons like that. Because there are times where you're just not getting better. So it's perfectly okay to stop a run of epochs because you're just not going to improve, right? So just be careful with that. Don't think that more epochs is the automatic road to better accuracy, lower loss, things like that. If you do believe that, or if that was part of your answer, I'm not going to call out anybody, but if that was part of your answer or part of your thinking, maybe you didn't give the answer, look at question number 2. What is the effect of adding more nodes to our layers? And if you want to think about that even harder, what is more likely to reduce or to improve your accuracy, improve your overall model? Is it more nodes or is it more epochs? Think about that one. What's the, nothing's guaranteed, right? But what is the higher probability approach that you could be using? Is it more epochs or more nodes? Think about that. Okay, so it's Abdalaziz. Okay, yeah, I remember you. You've been here before. I think you were from Pakistan, if I remember right. Let me know. But thanks for being here. Welcome back. Welcome back, Abdalaziz. Michael says lower learning rate might take a very long time to get good results, or get stuck before reaching the best solution. Michael, but they can all get stuck, right? They can all get stuck. You're right that it takes a longer time to get good results. But again, lower learning rate is not always a guarantee of a better result. Khalid says a high learning rate may also skip a minima. Yes, that's true, but that's still no guarantee of a better result because there could be multiple minimas, right? So I can appreciate where you're going with that, Khalid, but again, more epochs is not always more better, right? Okay, Abdulaziz says they're from Sudan. Sorry about that, but welcome back. Glad to see you here, my friend. Um, so so while you guys think about my other question, right? What is more likely to lead you to better results? More epochs or more nodes, right? Think about that. We're by proxy, we're hitting on a very, very important topic here. Do not assume that you're always going to get to a good answer with a neural network. Neural networks are very powerful. They're used quite a bit. They can be used on all types of data, but people take all of that and they assume that, oh, there has to be an answer we can get to. That's not always the case. That's not always the case. You are not guaranteed results. You can get pretty good results, but you are not guaranteed perfect results. And the reason I bring that up is because for those of you that have seen my content before, you guys know that there are some things in data science that I don't always agree with, right? And I don't always agree with some of the approaches and technology out there around automated self-driving vehicles. You know, Tesla and the FSD, Waymo and the Driver One or whatever they call it, OneDrive. Do not fall into the fallacy that machine learning and neural networks can solve everything. There is no guarantee that you're going to get good results that fit your use case. You can try different things, you can experiment with different things. That's part of being a data scientist. But to me, people who are working on self-driving cars are all working under the fundamental assumption that there's nothing that machine learning and neural networks can't solve. Who said that? Why does that have to be true? That doesn't have to be true at all. There can be plenty of unsolvable problems in data science, right? Now, for most of us, we're going to work on problems that can reach a conclusion, or at least maybe not perfect results, but acceptable results, because they don't kill anybody. They're not going to have any physical effect on somebody, right? You know, if you take a neural network and you misclassify a document, you know, nobody's going to die over that, right? But definitely have a healthy sense for the understanding that you are not guaranteed great results. There are going to be times where you're going to have to say, hey, we spent some time on this. We did our proper experimentation, and this is the best we could come up with. That's totally okay. Michael says, I would say more nodes. Okay. Fabrizio says, I will say more nodes. Nodes act as neurons and may capture global patterns and get this in the first layers. But if you had more layers, you may get deep learning. More nodes might help, but is not enough. I think you meant to say more epochs, but might help, but it's not enough. Let me know, Fabrizio. Vibab says, depends on the current state of the model, but if performance, you mean making our model smarter, then it'd be increasing the number of nodes. Yeah. Yeah, so the three of you are kind of hitting on that, and I think you're right. It's the number of nodes is much more likely to improve your accuracy, right? But as question 2 indicates, adding nodes does not come without costs, right? So what is the effect of adding more nodes to our layers? So let me know in the chat. What is the effect of that, right? So Fabrizio says, Waymo uses convolutional neural nets for perception and reinforcement learning for planning, movement. He studied mechanical engineer, and they are using both mechanical engineering and machine learning. Yeah, okay, that's all fine and good, Fabrizio, but there's still no guarantee that something good's going to happen, right? I mean, there are still some unsolvable problems in machine learning and data science, right? Vibob says complexity increases. Yeah, yeah, absolutely. Adding more nodes to our layers absolutely increases the complexity, which also means increased processing time. It's a bigger neural network overall, like literally in file size. It's going to affect your runtime times, right? In most scenarios, you won't need something that needs like microsecond level response times, but in some cases you might, right? But yeah, the complexity increases, but a it's more probable that you're going to get a refined neural network by adding more nodes to our layers and even adding layers than it is to say, well, I'll just run more epochs, right? So yeah, I think you guys are on the right track there. Okay. So if you want to think about this slide a little bit more, go ahead. That's totally fine. But let's think about this next slide. I posted this on my Instagram earlier this week, and it kind of got crickets, and that kind of disappointed me, guys. Because to me, everybody's asking me like, oh, Dennis, how can I improve my data science? How can give me a project idea? But like data science is all around you guys. Like you should be able to have a critical eye to so many things around you. So I saw this post on X and I saw this last line caught my eye as a fun little exercise to think about. So this person is quoting, I guess this is like a Tesla press release or something. The neural nets for Optimus are larger than what Tesla uses for Auto. Okay, so just so we're clear, Optimus is their humanoid robot that they want to deploy. And Tesla obviously is using the full self-driving, right, the FSD. Neural nets for Optimus are larger than what Tesla uses for Auto. So this is a great opportunity for you to apply your own critical thinking. We have learned enough in the last 4 weeks here where we should be able to make an intelligent decision on this. Okay? So we're going to role play like we're Wall Street analysts and we want to evaluate, this statement. Your boss asks you, as you're a business analyst, you're a financial analyst, and your boss asks you to evaluate this statement. Neural nets for Optimus are larger than what Tesla uses for Auto. I want you to think about that. And if you're having trouble with that, I'm going to give you a hint in about 30 seconds. But I want you to think about that because you should be smart enough, right? Well, first of all, this is the kind of stuff you should be doing as a data scientist anyways. I always have a critical eye. But right now, you should be able to make an intelligent conclusion on this. Whether it's right or wrong, we'll put that aside for now. But it's more about, can you draw a conclusion and what's your rationale, right? So guys, in the chat, give me your best, hey, I'm a data scientist, I'm a data analyst, here's my thought and here's my rationale. So think about that and put it in the chat. So Osama says, more nodes allow the network to learn more complexity, but too many nodes can cause overfitting or a vanishing gradient. Yep, I'd agree with that. I think you're on the right track there, Osama. Michael says, increases computation, can improve accuracy, increase the network's capabilities for complex patterns, and may also cause overfitting. Yeah. Michael, I love how you put a plus and a minus for each point you made, right? It can improve accuracy, but it does increase the network's capabilities for complex patterns, but it may also cause overfitting. So yeah, I like that. All right, guys. So neural nets for Optimus are larger than what Tesla uses for Auto. What do you guys think? And guys, if you're over on Instagram, feel free to say hello. Feel free to join us over on YouTube. It's up to you, okay? I'll give you guys another bit of time. Think about this. Um, the neural nets for Optimus are larger than what Tesla uses for Auto. Um, Yassine says, hello, sir. A late Yassine from Tangier, Morocco. Yassine, don't worry about it. Good to see you, my friend. Glad you're doing, hope you're doing well out there. Glad to see you. Um, Yassine says, what is Optimus? Yeah, so for those of you guys that aren't familiar, Optimus is the humanoid robot from Tesla, right? That personally I think is going to be vaporware for a long time. But reasonable expectation that it uses a neural network. So they're saying that the neural networks for Optimus are larger than what Tesla uses for Auto. Fabrizio says, what does it mean? I think increasing neural nets doesn't change anything. It has to do with the quality of data and research expertise, not neural networks. The big problem has always been data. Yeah, Fabrizio, but your boss doesn't care about that, right? Your boss is looking at this statement and wants you to make a decision on it, right? So let's focus on the task at hand, right? So let me give you guys a hint. When I think about this, I think to myself, what does the output layer look like? So that's your hint. Start thinking about the output layer. What does the output layer for each one of these look like? Yassine says, I don't know what to do. I intend to do by saying that, but for me, it makes it worse. Yassine, I'm not sure I fully understand your question. But so Yassine, just to be clear here, right? The task in front of the chat right now is to evaluate this statement, right? This is part of a Tesla press release that was out earlier this week, and they're claiming that they have these two products, right? Optimus is the humanoid robot, and the Tesla, FSD full self-driving car, right? Both of them is reasonable to expect they use neural networks. And they're saying that the neural networks for Optimus, the robot, are larger than what Tesla uses for Auto. Vibob says, I think Auto is still a fairly narrow task compared to a machine that is supposed to imitate us. Okay. Define narrow, Vibob. Fabrizio says output for Tesla might be object detection using CNN, and for Optimus might be reinforcement learning. Both of them are different. One is predicting the other is generative unsupervised learning. I'm trying to fully understand your answer. Why would the Optimus be reinforcement learning? What makes you say that? And if it is reinforcement learning, wouldn't the Optimus neural network be smaller? I think it'd be smaller, right? Because a reinforcement learning neural network you can grow over time. right? Yassine says to tell me that a humanoid robot has a bigger neural network than self-driving car, meaning they are more efficient, is completely irrational. What do you mean something can make an error? Make an error can end me is less efficient than something that has more tolerable errors. Okay. All right. So Yassine is looking at this from the error side, right? Because as we've talked about, more layers, more nodes should lead to better accuracy, but it does lead to a bigger neural network, right? So yeah, so okay, so Yassine is saying, well, look, Optimus has a much bigger margin of error, right? Whereas the Tesla, the car, has like zero margin of error. So Yassine, stop me if I'm misunderstanding you, but Yassine is saying, well, if the car has a lower margin of error, like zero margin of error, that means it's more nodes, more layers, all of that, right? And we know more nodes, more layers, more computation means more hardware, means bigger files. So Yassine, if I understand you right, Yassine would disagree with this statement, right? In a way, Fabrizio's previous one would also disagree with this statement because if Optimus is reinforcement learning, then it would presumably start off smaller, right? So Parth says, Elon once said during an AI day that a humanoid robot essentially needs to run FSD for legs and arms, meaning control of its entire body with real-time decision making. Okay. Which is even more complex than controlling a car with a fixed set of inputs and outputs. Ooh. Parth, you had me in your first statement, you lost me in your second one. A fixed set of inputs and outputs. I don't know about that. Is the world a fixed place? I don't know, Parth. I think that and I don't want to be putting any words in anybody's mouth, but I think Yassine would disagree with you, right? Yeah, Parth, you kind of lost me in your second statement, my friend. Fabrizio says Optimus is human in the loop. It's used to optimize reward and loss policy with each correct movement of the robot. You are not predicting, but improving movement. Yeah. Put that aside, though. Answer the question, right? You're making your boss fall asleep, right? You got to answer the question, right? So, I like that, a lot of you guys are putting some rationale behind your answers. So remember that I gave you the clue of think about the output layer, right? So when I say thinking about the output layer, I'm kind of referring to the different objects that have to be recognized by each one of these, right? If I'm in FSD, I have to recognize every possible object that's coming at me in a driving situation. Versus an Optimus that has to recognize every possible situation. But is that a home? Is that a factory? Is that outdoors? Is that indoors? Now, Tesla is obviously going to tell you, oh, we're going to be able to hit all of those use cases for the Optimus. But can they really? But let's stick with the cars, right? How many objects does a car have to recognize? Like a neural network in a car have to recognize? And if you think about each one of those being an output layer, right? Or an output node within the output layer, is that likely to be a short list or a long list? And I think about that because there's no requirements or no restrictions on it, but there's likely to be a correlation between the size of your output layer and all the other layers, right? You're not going to have 1,000 output layers and 1,000 output nodes, and your hidden layer is only going to have 3 nodes, right? Like usually not considered a good neural network design pattern, right? Vibob says narrow for self-driving cars is just an advanced cognitive problem, but for optimists, the world is more physical, more varied interactions. Um, maybe. Yeah, maybe. Leo, so good to see you, my friend. Leo says, "Hi, everyone. Hope you're having a great weekend so far." Yeah, I think we are, Leo. Thanks for being here. Good to see you. Let us know how you're doing. Parse says, "What I meant by fixed was inputs, camera feeds, radar, lidar, GPS, speed sensor, etc. Outputs, steering, angle, acceleration, braking commands." Parth, but that's only one part of the potential outputs. You got to recognize what's around you first, right? So, what about just like object detection, Parth? There's almost certainly an object detection neural network, right? Yassine says, "It's true that the humanoid robot requires real-time decision making, but so is a self-driving car. However, for the latter one, the span of possible scenarios is much larger." Okay. So Yassine is arguing, hey, there's more situations in a car than there is for the Optimus, right? And coming back, I think it was, I'm not trying to call anybody out here, but somebody mentioned how you also got to control the arms and legs of the Optimus, right? So I think the counter argument to that is that yes, those are algorithms, but are they neural networks? Because not every algorithm is a neural network, guys, right? To me, that would strike me as more of a traditional like mechanical algorithm. I don't need a full-on neural network to tell me that I got to turn a mechanical leg, 30 degrees and take a step forward. That's probably not a neural network, right? That's probably like, it's probably just like math, right? Like engineering math. So, are they using neural networks for that? Maybe, but it seems unlikely, seems inefficient, right? So that's got to be part of the rationale too, right? So Parse says, in a humanoid robot like Optimus, the robot has many more degrees of freedom, way more outputs to control. The sensory inputs can be more varied and complex. Parse says, kind of forgot about object detection. Yeah, Parse. So that's why I gave you guys the hint. Start with the output layer, because the output layer is what is the prediction of the neural network, right? And if I'm an FSD car and you're giving me all these images, right? Because FSD is camera based, I gotta know, is that a cyclist? Is that a pedestrian? Is that a stop sign? Or is that just a red light? Am I in between the lanes? Is there a car next to me? Like you got a lot of objects coming at you, right? So is that likely to be a small output layer or a large output layer? Fabrizio says 30% machine learning, 70% mechanical engineering. Yeah, I'd agree with that, Fabrizio. Yeah. Not everything's a neural network, guys, right? We can't rush to always go to a neural network solution. Let's bring it back to our friend Parth. Because if you guys remember, Parth was asking about neural networks in a video game. And I think that there's a lot of ways you could be using neural networks in a video game, right? But think about everything we just talked about. Is there a danger to using a lot of neural networks? Because you can use a neural network for object detection in a game, for the NPC control that Parth talked about, for some of the scoring elements, for some of the rendering elements, as far as how different worlds or different screens or whatever are created. But is there a downside to that? What's the downside to that? You guys should know the answer given everything we've talked about, right? Starry Vibes. Starry Vibes says, hello, sir. I hope you're well. I'm doing well, Starry Vibes. You're late. Just kidding, Starry Vibes. Hope you're doing well. Hope your studies are going well. Glad you could join us. Delio, what are your thoughts in Strata Scratch? Hey, Delio, I usually don't take individual questions on Sundays. It's more about the series. So if you want to join me on other days, you're welcome to stay for neural networks, but I don't really take individual questions on days like today. But Delio, if you do want to participate, the answer right now, the question in front of the chat right now is, why not just use neural networks for everything? As I said earlier, I think that some of the elements in Optimus are probably more just like mechanical engineering math. Like they're probably not using a neural network to move the arms and legs. I'm guessing that's low probability. Why? Why? And then also, guys, we haven't really reached a consensus on the screen, right? Neural networks for Optimus are larger than what Tesla uses for Auto. That should stop you in your tracks if you're a data scientist of any level, right? Like you should be able to apply critical thinking to that. So I think that Yassine is one of the few that's given, like Yassine has basically given an answer. He's planted his flag, and I love that. I love for the data scientists that work for me to plant a flag and say, hey, I think this is the answer right here, and this is why, and this is what I'm sticking to. So come on, guys, give me your final answer. Talk to me like I'm the CEO. Don't give me that data science nonsense. Plant a flag. What's your answer here? Hart says, I once asked my professor regarding an idea I had, which was that what if we use neural networking to increase storylines possible? Like different endings operate about what the player does in game. Okay. Why wouldn't you do that? What is the case against that? Is there a case against that? Maybe there is, maybe there isn't. Though that idea was rejected by saying it'll be way more complex to handle, and the possibilities inside the game will be infinite, and sooner or later I'll be facing a game crash. Okay, why would you be facing a game crash? Like everybody should basically know this, right? Like why wouldn't you just put everything in a neural network? Right? All right, so I'll give you guys another 30 seconds here to plant a flag here and let me know what you're deciding on in terms of what you're seeing up on the screen. That is what I want to know, since my professor kept dodging that question by saying just try it out. Okay, well, that's not bad advice, right? Sometimes you learn more by getting burned, right? So guys, I mean, come on, the answer is performance, right? We just finished talking about how some of these neural networks, you got to be careful with the size of the nodes, right? It increases your footprint. It can potentially, well, it definitely will slow down your training time. It could have an effect on your runtime predictions, performance, right? Okay, so Michael is saying, given the challenges and complex requirements of developing a general purpose humanoid robot, I think it's reasonable to agree that the neural network powering Optimus would be larger and maybe more complex. Okay, Michael, so I see your conclusion, but help me understand your rationale a little bit more. So your rationale is because it's a general purpose robot? But I mean, couldn't I just tell you that a Tesla is a general purpose car? Right? I mean, I can put a Tesla in a lot more varied situations than I can an Optimus, can't I? Like it's very unlikely that an Optimus would ever have to deal with rain, right? Or low light conditions. Like, because does anybody have a use case for when an Optimus will be operating at night? Like in low lights, right? Like obviously at night inside a well-lit factory is no big deal, but like at night in low light conditions, like what's the use case for that? You're gonna have the Optimus mowing your lawn at night? Like, but I can think of a lot of situations where I'll be using my car at night in the rain, in the snow, right? So I personally tend to side a little bit more with Yassine, right? Because I think about that output layer and all the different things that a car has to recognize. And I'm thinking, wait a minute, that's a lot. Fabrizio says, I think neural nets for Optimus are not larger than for cars. Mechanical engineering can help fix some problems without large computing. Second, reinforcement learning doesn't involve large neural network process, assuming this is used for robotics. Okay. So Fabrizio, you're sticking with the reinforcement learning side of it, and that's okay. I guess I really can't comment on that because I hadn't heard that they would be deployed in a reinforcement learning state. Now, obviously, they're using reinforcement learning now during training, during like the pre-purchase or the preparation of Optimus. But I didn't think that would apply when you actually buy one, right? They should already come trained for the majority of tasks, right? But, I can appreciate that you did provide a rationale. So yeah, so Fabrizio, Yassine, and I are kind of like going against the statement here. Right? We're probably saying, hey, we disagree with this. This doesn't smell right. Right? We're getting there via different rationales, and that's completely okay. But yeah, so we have at least three of us disagreeing. Michael, so far, is the only one I can see that is agreeing with the statement. He can see a path to why Optimus would be larger than what Tesla uses, right? So I think is it Naren? Let me look, because I know you said your name earlier. Was it Naren? Yeah, it's Naren. So Naren says, I think you'd need a bigger, better neural network for the car than the robot, keeping in mind that a mistake in the car will cost lives, robot less chance of a life getting affected. Yeah, okay. Okay, Naren. So Naren is also on team disagree here, right? Where because the auto neural network needs higher accuracy, higher recall, higher precision, higher everything, it's going to be a larger, more layers, more nodes, all of that, right? So yeah, I'd agree with that. So that's four of us disagreeing with the statement with three completely different rationales. So that's great, guys. This is exactly the type of conversation that you should expect to have in a data science team room, right? That's kind of like what we're simulating here, right? So this is good, guys. This is good. Whoa. Michael's saying, I also agree with the points you raised as well. Now, Michael, come on. You can't back away from what you said before, buddy. When you plant a flag, you got to be willing to fight for that, right? Discourse is a healthy thing on a team, right? So don't back away on me now, buddy. Come on. You got to stick with what you said. Michael says, what do you think about the demands of embodied AI in the future being fundamentally different and arguably more encompassing than those of autonomous driving? Help me understand what you mean by embodied AI. Because you're giving a very specific example of autonomous driving, but you're not giving us an example of the embodied AI. Because also one thing we should remember, guys, autonomous driving isn't necessarily AI. It's much more on the machine learning side than it is AI, right? So keep that in mind, Michael. Give me a better summary, if you can, on what you mean by embodied AI. So Leo says, the idea of EVs performing in a safe, functional way, from my perspective, can't be achieved without considering a whole integrated road system that can optimize the mixed algorithms performance. Same with Optimus. I don't like the idea of a humanoid robot built for general purpose. Okay. All right, Leo, I can appreciate that. But Leo, where do you stand on this section, on this statement, though? Because you're right, you're describing like the utopian scenario, right? Like the ideal use case. But we most likely won't achieve that, right? Like, Elon Musk isn't sitting around waiting for road improvements or road sensor improvements or whatever, right? And obviously that'd be a large scale project anyways. So we can only really take what's in front of us, right? So what's your take on this actual statement? What do you guys think? Last call for statements on this, and then we're going to move on. The last call for planting a flag. Michael, don't back up on me now, man. You gotta stand by your guns. You end up respecting somebody who can say, hey, you know what? I hear you guys, but I got my position. I'm happy with my rationale. This is what I believe, and that's what I'm going to stand with. Don't be quick to bend, Michael. Don't lose on me now, man. All right, guys. So last call for answers. Last call for answers on the highlighted section. But most of us are on team disagree, right? Most of us do think that the car would have the larger neural network. Or if you're shy, you can just say, hey, I'm on team disagree also. You don't have, or you're on team Michael, right? I guess team Michael would be team agree, right? But it's healthy to have a rationale. It's healthy for us to have this discussion. Again, I'm using this as an example for different things that you guys could be picking up in your daily readings, in your, articles, your social media or white papers. You should be picking this up and saying, hey, I'm a data scientist. I know enough to answer this. Let me form my own opinion. Let me, exercise my data science skills here. Okay, so Leo is on team agree. I agree with Optimus having the larger one. Optimus was designed to have general purpose and handle much more than cars. Okay. So Leo thinks, so Leo and Michael are on the same team there for team agree. Manoj is joining team disagree. I agree with you, Sir Dennis. Yeah, thanks, Manoj. So we have a little bit of a split room, guys, and that's okay. But again, I think this was a fun exercise to go through because this is the stuff that I stop and do, right? When you guys tell me, oh, I want to do what you do, Dennis, I want to be a data scientist. This is what I do, right? This is something that just came up on my Twitter, for you. You can see I don't even follow this account. It's just something that came up. And you should have a critical eye for this to be able to catch up and say, oh, well, wait a minute. Whoa. What's this say? What's this say? I don't know if that's true or not. Let me think about that. I want you guys to have that thinking, okay? So Michael says, embodied AI is like giving that AI brain a body, a robot, for example. So instead of just existing as code in a computer, AI can actually move around, see, touch, and interact with the real world. Okay, I understand that as a concept, but is that what's being promised from Optimus? I'm not claiming to be an Optimus expert, but I haven't seen anybody out there who's like promising that as part of the output or part of the goal, right? Let me know. I'm happy to be wrong on that, but to me, I still view it as a a mechanical use of machine learning, right? I don't even view it as AI. Remember, guys, there's a difference between AI and machine learning, and machine learning is not AI. So keep that in mind when you think about these things. Leo says the generalization function requires a larger and complex neural network. Yeah, yeah, but I mean, I'm sure there's ways for us to quantify this. It just feels like a car has more objects to detect or more situations to make a conclusion on than an Optimus would. And I have nothing quantitative to back that up. It's more of just a professional opinion, right? But who knows? You might be right. Maybe there is a larger generalization function for a robot. Fabrizio says robotics are also using GANs to replicate right movements of the robotics compares to humans. It's a type of generative ML. This one requires more stops of a gradient, less computation, less nets. I've never heard anyone use the word GANs and less computation in the same sentence. If anything, it's more computation. So yes, GANs are being used. But I think that those GANs are probably heavier on the training side than they are the runtime side, is my guess. We need to understand the type of machine learning model they use better to make informed decisions, but I will say it uses less neural networks. Yeah, I think it's probably. Oh wait, Fabricius, you're still proposing this as an answer. Yeah, I agree with your conclusion, but I'm still not sure if I understand the path that you used to get there. Right? Because you could also say that the FSDs use GANs, right? Yeah, so I'd still like a little bit of a clear rationale and a little bit more of an understandable rationale, right? Because remember, sometimes when we're doing this, we're also practicing for the non-technical audience. So keep that in mind. Okay, guys, so I want to move on to the next slide. But this has been great discussion, right? And this is exactly what you should be having. And if you don't, you should be encouraging it among your data science team, right? You can have difficult questions and you can take reasonable answers to them, but you got to be able to back them up with your rationale and be able to explain your rationale, right? So good job on doing that, guys. All right. So this is not quite a lightning round review because this is a little bit kind of like a looking forward to some of the topics that I want to cover today. So 2 questions up on the screen. Feel free to answer either one. Let me know in the chat. 1, are there different kinds of neural networks? 2, what are hyperparameters and how can we adjust these? What do you guys think? Some of you have already mentioned, like somebody mentioned hyperparameters before in the chat. So what are they? How do you adjust them? Give me some examples or whatever you'd like. What do you guys think? So feel free to answer one of these, two of these. If you don't know these, that's okay. Like I said, these are a little bit of a looking forward type of questions. But are there different kinds of neural networks? And what are hyperparameters? How can you adjust those? What do you guys think? Give you guys another few seconds to think about these. So Leo says the cars would work more with classification problem algorithm levels today instead of clustering, anomaly detection, or either ranking problems. Just finishing the thoughts. Okay. Yeah, Leo, but that's part of the problem though, right? Because if you're saying classification problem, which I agree with, how many things do you have to classify? Isn't each classification class an output in your neural network? It's an output node, right? So that's why I said the hint previously was think about what your output layer looks like. Is that a small output layer or a big output layer? Right? So take what you just said about it being a classification problem. How many items are you classifying? Is that likely to be a small list or a large list? So Yassine and Manoj are saying yes. Yeah. Well, yeah. Okay. Yes. Give me more. Give me more than just the yes or no. Okay. All right. Starry Vibes coming in strong with an answer for hyperparameters. Hyperparameters are external configurations of a neural network, like a learning rate, batch size, epochs. Okay. All right. Manoj says CNN, RNN, FNN. Okay. Give me some definitions there. Give me some definitions. What's a CNN? What's an RNN? What's an FNN? Leo says it's a big one, but smaller than Optimus. Well, Leo, I guess that's where the crux of the question lies, right? I don't know if it's smaller than Optimus. I'm tempted to say that the car is bigger. There's so many things to consider in a car, right? And it's not just enough for me to say, oh, that's a speed limit sign. I have to be able to read and understand the speed limit sign, right? And then there's just so many variations. Like, is that a cyclist or a motorcyclist? Is that one cyclist or two cyclists? And then there's like road markings, right? Am I in a turn lane? Am I in between the two markers? Is there a crosswalk coming up, right? Like a pedestrian crosswalk? I don't know, Leo. It just seems like in a car, there's a million different images coming at you, right? Starry Vibe says, they're set before training and adjusted to optimize performance using techniques like grid search. Ah, okay. What's a grid search? What is a grid search, Starry Vibes? I like where you're going with this, but give me some more details. Fabrizio says, yes, give me some more details, my friend. Khalid says, yes, like CNN, RNN, FNN. So Khalid, a good answer, but give me definitions for those. Hyperparameters are the configuration settings before training a machine learning model. Okay. Hyperparameters are parameters that can't be optimized mathematically with some predefined rule and have different optimal values for different problems. Okay. Can't be optimized mathematically, but that's everything in the world, right? Um, Feed forward and then simple basic structure of input, hidden, and output layers. Okay, keep going, Manoj, keep going. Fabrizio says hyperparameters are fixed values used to initiate the feed forward backward propagation on neural networks. Ooh. Is that all they do though? Is that all they do, Fabrizio? Feels like they do a lot more than that. Let's see what Starry Vibes come up with, because Starry Vibes is on the right track. Starry Vibe says it's a method to find the best hyperparameters by trying all possible combinations from a predefined list. Okay, so that's Starry Vibes answering to what is a grid search. Manoj says CNN's image and spatial data convolution neural networks to detect patterns like edges, textures, and objects. Okay. Okay. All right. So let's think about what Starry Vibe said. So Starry Vibes was answering the question of what are hyperparameters, right? Hyperparameters are external configurations of a neural network like learning rate, batch size, and epochs. They are set before training and adjusted to optimize performance using techniques like grid search. They are set before training and adjusted to optimize performance. Okay. And then I asked, what is a grid search? And grid search is a method to find the best hyperparameters by trying all possible combinations from a predefined list. Okay. So hyperparameters are variables that we can set, a collection of variables that we can set and try them before, set them and try them during training. And we are adjusting them to optimize performance. In addition to that, we are coming up with a predefined list of values for all of those. And then we're trying the different combinations via what Starry Vibes is telling us is called the grid search. Okay. So I agree with that definition, with all of those definitions. Doesn't that sound like something, guys? Let me know in the chat. Doesn't that remind you of something? It's a bunch of predefined variables that we can set, and we can try different values during training for model optimization. That just feels like something, doesn't it? Doesn't like remind you of something? What do you guys think? Let me know in the chat. What is that? Like what are we doing? Like why does that even exist? I'm thinking of a word, guys. It sounds like something, doesn't it? Fabrizio is CNN as image recognition, RNN word by word prediction. Maybe. Let's make sure that we're not jumping to the uses, guys. We gotta think about the underlying reasons why these things exist. Like, why do we even need different ways of neural networks? Like, why? Fabrizio says you can do grid search or random search to adjust the configuration of hyperparameters to improve. Yes, that can be done too. Okay, Naren says weights. Naren says choose the weights to reduce loss. The best weights to reduce loss. Yeah, okay. But Naren, doesn't it feel like it's something? Kunal over on Instagram. Hi, how are you? Welcome. I think you've been here before, so welcome back. Hope you're doing well. Let us know how you're doing. But guys, this feels like something, right? Ooh. Ooh, um, Fabrizio, I'm not sure if I'm feeling this answer. Um, aren't you doing this during any training cycle though? I'm encouraging guys to think about this on a meta level. Like, why would grid search even exist? I'm thinking of a word here, guys. Oh, starry vibes, you're so close. Because different problems need different architecture. Oh, Yassine, you're so close. Like a Monte Carlo simulation. Okay. Oh, Khalid. Khalid got it right on the nose. We need different kinds of neural networks because we have different data types. Aha. Khalid, I love that explanation. We're going to come back to that, Khalid. We're going to come back to that. But Khalid, you're coming up with a great answer. So Khalid, if you want to go 2 for 2, what is the answer on, everything that Starry Vibes told us and everything everybody understands about grid search and hyperparameters? What is that? Why does this even exist? Starry Vibes, you're so close because different problems need different architectures. And Yassine, it's like a Monte Carlo simulation. Both of you are super close, super close. But think about it on a higher level. Like, what are we doing here? Like, why? What is this? So why are we even bothering with grid searches? What do you guys think? Why are we even bothering with any of this? Give you guys another 30 seconds. Yassine says optimizing the model. Yeah, that's the goal. But why? Like, what's the purpose of that? What do you guys think? Another 30 seconds here, and we'll get going with this one. Khalid says grid search is like a tuning technique to find the best combination. Yeah, okay, but why? Search tries all combinations in the grid to see which one gives the best performance. Yeah, but why? Like, what are we doing? What are we doing? So guys, to capture all the possibilities. Yeah, but why? Why? So guys, here's the answer. Very important. Write this one down. The reason why we focus so much on grid searches and what it means and the process of it is because this is where it's the experimentation of data science. Grid searches essentially represent the experiment side of the scientific process. What do I always tell you guys? When in doubt with data science, you always return back to the scientific method, right? In the scientific method, you make an observation, you form a hypothesis, you collect your data, and then you run experiments on your data, right? So this is us in the lab doing the experimentation side of data science. That's why you do this, right? So we're not chemists, who sit there and mix beakers and Bunsen burners and all that. We work with data. So grid searches is the experimentation side of being a scientist. That's really the big takeaway here, right? Very important for you to view it that way, because it should change your perspective on how broad and how frequent you want to do your grid searches, because your grid searches is basically the core of everything that we do as data scientists. Now, we're focusing on neural networks for now, but part of that experimentation is also trying it across different models. But even within those models, you're going to be doing grid searches because you don't know what version of that model performs best. But that's you being in the lab with your white lab coat and all that, running your experiments. So it's very important for you to view it that way, to say, hey, wait a minute, I'm a scientist. I run experiments on my data. It just so happens I do it with code and I call it grid searching, but these are my experiments. So every time you run these, every time you run a training cycle, every time you run a series of epochs, that's an experiment. So when I tell you guys data science is a science, we should be following the scientific method. You should be constantly experimenting with your data, asking questions of your data. This is it. This is where the rubber hits the road when it comes to the experimentation side of data science. So keep that in mind, because that is really what's this is where the work is, right? This is where you're separated from everything else. You can even think of it this way, right? When people say, oh, well, data scientists are also just coders, or I'm a coder, I can also be a data scientist. Grid search is unique to data science. You don't do grid searching, or if you're a software engineer, right? Because software engineers don't run experiments, data scientists do. Data science requires experimentation. Software engineering doesn't really do that, right? So keep that in mind, because this is where you're running experiments. This is your lab. You should be keeping track of these experiments. Just like a chemist would write down and say, oh, this time I'm going to use 10 milliliters, but last time I used 5 milliliters or whatever. We're doing the same thing. Oh, this time I use this learning rate. Now this time I'm going to use this other learning rate. This is where data science is running experiments. Super important for you guys to see it that way, because then you start to understand the importance of it. You guys with me on that? But just keep that in mind. You should have a permanent connection in your brain. When I'm talking about grid searching, when I'm talking about trying different hyperparameters, those are my experiments. That's me working in my lab, in my hey, I don't know what the answer is, but I'm going to find out by running experiments. That's that phase, right? Your grid search phase. You guys with me on that? Super, super important concept. And we see this, I think you can see it more clearly than you can in other models. Like you can get a sense of this from other models like regression methods, right? But you really kind of understand it the most here in neural networks because grid searching is such a defined portion of what we do in our code. Okay? Khalid says it automates the trial and error process. Yeah, sure. Instead of checking every possible combination like grid search, random search picks random combinations of hyperparameters from your given ranges. Yeah, yeah, sure, but like, why would you need to do that? I mean, if you're pressed for time, maybe you would do the random searching, but that's part of the advantages of using code, right? That you can try every permutation in a relatively short amount of time, right? Or a reasonable amount of time. Fabrizio says data comes in different forms, can be x squared. So it distributes different ways and you can capture those patterns better with those techniques. Okay. I could see that. Salient, I think it's your first time, so welcome. Grid is like iterating from beginning to end with every possible parameter. So large data sets means slow process. Random is more advantageous. Maybe, but that's only if you need it, right? If you're pressed for time or if you have bad hardware or whatever, okay. But there's going to be situations where you're going to have plenty of time and plenty of hardware. So I don't think that holds to say that random is more advantageous, right? Parth says, I mean, it's faster. Faster for what? Like you can't always say that, especially if you have a large number of hyperparameters, right? Because you're going to have interaction factors, right? Interactivity factors. So just because you hit on one random combination that kind of sort of works doesn't mean that like doesn't mean that you're any closer, right? Doesn't mean like the next combination up is going to be better, right? So I don't know if I'm buying that, Parth. Okay, so here's what I want to do. I want to go back to some of our code. We are going to continue working with our little toy example that we had before. Do you guys remember, if you were here last week, you can remember that we were getting some pretty good results with something like this, right? We were using hidden layers, some output layers. We know that we're doing an XOR table. This is our training data and our expected outputs. And we were messing around with the learning rate, with the epochs, and the hidden layers, right? So think about everything we just said. When we were messing around with our learning rate and we were messing around with this number here and messing around with the epochs, what were we doing? What's that called? Let me know in the chat. What in retrospect, right? Because we didn't talk about hyperparameter tuning last week or grid search last week. What were we doing what were we doing then? What was that called? What were we doing? Michael, you're the man. Yeah, we were experimenting. Yassine, that's right. That was us wearing our white lab coats. We were trying different mixtures and all that was us running experiments. That was us doing a portion of hyperparameter tuning. It was a manual way of doing it. We didn't really adjust code, we adjusted variables. But guess what? There's no requirement on what you have to do that, or on how you have to do it. The point is that we were applying the scientific method. Hey, let's try this. Oh, geez, that didn't work so well. Oh, that was terrible. Let me go in the other direction. That's still experiments. That's still hyperparameter tuning. That's still maybe not quite grid searching because we weren't going about it in an orderly fashion. We were just kind of guessing. But we were experimenting. I mean, this is the scientific method for data science. Right? Like, that's the beauty of what we were doing. Okay, Yassine says lesson taught. Yeah, so I think you guys see where I'm going with that, right? And this also ties back to something, what I told you guys before, where for me, when I learned neural networks, that's where data science like really took off in my mind. Like I was already into it, and I was already like I already taken a few classes and all that. But like when I saw like the neural networks and the architecture and the activation functions, and then seeing the grid search, that's where it was like, oh man, I understand why they're so powerful. Because now you can run like 1,000 experiments in like 10 minutes. Like that's part of the power of neural networks and grid searching in general, right? All right, so I'm trying to think about what this looked like for us before we did adjustments. I want to say that was 20. I think I want to say it was 2. And then I know this was 10,000. So I want to tie, give me a second here, guys, to experiment. Because I want to tie this back to the last thing I want to teach today. Okay. Is that what I wanted? Yeah. Okay. So I made some modifications. If you guys remember, last week, we got to some really good results, right? We got to a neural network that was viable. This is kind of where we started. I think I got most of the parameters correct. So first of all, real quick, is this a good neural network or is this a bad neural network? Just give me a 1 if you think this is a good one. Give me a 0 if you think it's a bad neural network. Give me your answers real quick in the chat, and then we'll get to talking about where I'm going with this. There is a method to my madness, guys. Okay, so Yassine is voting 0, 0 for Michael. Starry Vibes also a 0. Ooh, Salient. Guys, somebody go check on Salient. They got a bad keyboard. They meant to write a 0, but they wrote a 1. Okay. So yeah, I'm seeing a lot of 0s in the chat, and I think that's right? The loss is not great, and most of you are probably already keying in on here, right? This is not great, right? And we know that because we know what our input data looks like, right? Let me go back to that. We know that we are just training on a simple XOR table. So if you guys aren't familiar, this is from the world of Boolean logic, right? Boolean logic and XOR would tell you that you only need one or the other to be a 1. If both are on or both are off, it's a 0, right? This is our training data. Just Watcher, I think it's your first time here, so welcome, glad to see you. Just Watcher did not say anything, they just voted, so username checks out. Okay, so we know that this is our output, right? Or our desired output in our training data, right? Okay. And if you guys have been here before, you remember that I told you guys that my eye brought me to these two results. To me, this is a sign of a terrible neural network. So let me know in the chat, why should that catch your eye? Why am I saying that that's a really bad sign of a bad neural network? Just Watcher says, yes, sir. Well, glad to have you here, Just Watcher. If you want to just hang out, that's totally cool. A lot of people do that. Alien says, I heard it wrong. Sorry. No worries, my friend. No worries. We were going to send a search party out there. Make sure you were wrong. Make sure you were okay. Salient just created an off by one error. Yeah, but here's the thing, Khalid, that on most keyboards, the 1 and the 0 are really far apart, right? So, I don't know. Being the outlier. Okay, I can get that. I can be down with that. Okay, guys, so what's wrong here? Why did I tell you guys that these two lines caught my eye? What catches your eye that tells you that, ooh, this may not be such a good neural network? Michael says too far apart. Give me more information on that, Michael. You're implying they should be close together. Why should they be close together? Right? Or anybody else. Why would these two lines catch my eye? I'm saying that, as I'm a trained professional here, guys, right? So to my professional eye, this catches my attention. Why is that? Why should it catch your attention too? What do you guys think? We're going to go over 2 hours again, guys. Guys, we need to talk, guys. I'm an old man, guys. You're making me go for 2 hours on a Sunday morning? On a Sunday morning, on 1 cup of coffee. You guys are making me talk for 2 hours? You guys are so mean to me. Why should this catch your attention, guys? Okay, so Fabrizio says different problem, same class. Actually, I meant to say different probability, same class. Oh, yeah, and that's exactly right, guys. Right? Huge red flag. We know that these two resolve to the same output of 1 in an XOR table. Right? But yet, we're so far off on those classifications. So Fabrizio's right? It's different probabilities for what's essentially the same class, the same output. So that's a huge red flag, right? Okay. The second reason why it's such a huge red flag is over here. Look at those inputs, guys. So even just like not from a data science, just from a general perspective, like you're telling me that 0, 1 gets me a 0.5, but 1, 0 gets me a 0.97? Same number of inputs, same input, same value of inputs, but I just reversed them. And you're telling me that that gives me completely different results? What? What does that tell you guys? And keep in mind, I just asked you guys, are there different types of neural networks? And I think the most reasonable answer somebody said was, well, because there's different types of data. So think about that. And then think about what I just told you here. 0 and 1 and 1 and 0, same number of inputs, same value of inputs, but reversed. What does that tell you? What conclusions are you able to draw from that? Right? If we put on our scientist thinking caps, what is the conclusion we're drawing from this experiment? Because we just ran an experiment, right? And you don't have to think about it from a like a neural network expert. Just think about it as a data science student. What does that tell you? Same class, same class. They should give same probabilities. Yeah, Fabrizio, I'm with you on that. But let's focus on the 0, 1, 1, 0. What does that tell you guys? What is and you can start by thinking, well, what is the only difference there? You can clearly see it's the same number of inputs, 2 inputs, same value, 0 and 1, but they're reversed. So what does that tell you? What do you guys think? Okay, Yassine. Yassine says, I mean, the conclusion I got is that order matters to that network. Yeah. Just Watcher says, yeah, order matters. Leo says data pre-processing failed. Maybe Leo. But yeah, Just Watcher and Yassine, I think you're on the right track. Because that's the only difference, right? The only difference is 1001. If you guys want to sound all like data science professional about it, that's known as a sequence. Sequence matters. Right? That's basically what we've concluded here, right? That's what this shows us. Give me just a second here, guys. Sequence matters. That's what we've learned. So, we're 1 for 1 here, guys. Let's go 2 for 2. Sequence matters. And we just said that there's different types of neural networks, right? What should our next experiment be? This is only one type of neural network, guys. It's a very simplistic one. We're not using any frameworks. We're not using a lot of data, right? It's a very small data set, right? We're not using, anything fancy, really, right? I mean, the whole thing is like what, a couple hundred lines of code, right? It's 86 lines of code. So I should have said a couple dozen lines of code. But what should our next experiment be? Okay, Yassine says we need to try a more sequence compatible architecture like an RNN. Yeah. Perfectly reasonable conclusion, right? So I'm walking you guys through this so that we can understand the thinking process that we should be exercising as data scientists, right? Because we're not changing the data. The data is what it is. But we can change our experiments. We can run experiments, draw reasonable conclusions to shape our next experiments. Right? Nothing wrong with that. So yeah, we can do that. So let's take a quick second here to calibrate our understanding. Why would Yassine have suggested specifically an RNN? So there's CNNs and there's RNNs. Does somebody want to give me the most basic explanation possible that they can of what a CNN is versus an RNN? And why would RNN fit this need. Hint, if you wanted to, you could also make the argument that a CNN fits this need. If you wanted to. But what do you guys think? Because I'm in agreement that an RNN makes sense here. But you could also make an argument for a CNN. Why am I saying that? Some of you guys already had the answers in the previous section. So just think about your previous answers. Okay, so Salient says CNN is for unstructured data, images, RNN for sequential data. Khalid says, because can process sequences and remember order. Okay. Anybody else? Okay, I'm sorry. Maybe I didn't read Part's answer. CNN says best for images, spatial patterns. RNN best for sequences, time-based patterns. Okay. Anybody else? Sorry guys, I moved my console off the screen. Didn't mean to do that. Fabrizio says, use an MLP multi-layer perceptron. Maybe. Isn't that a little bit of a overkill for 4 different inputs? Maybe a little bit of an overkill. Okay, but most of you guys are on the right track there, right? Where you want to use something that's more for sequential data, right? CNN is more suitable for images. It can also be used in variation. CNN for one-dimensional data as the input we have. Okay, so Yassine, I think you're hitting on you're the one closest hitting to the point I'm trying to make here. So remember that I referred to it as sequences, right? But sequences can be, one-dimensional or multi-dimensional, right? So for those of you that are recommending the RNN, hits upon what Yassine is talking about where RNNs are good for single dimension, right? Like a time series would be, right? This happened period 1, period 2, period 3. It's one dimension, but it's sequential, but it's one dimension, right? But images are not like that. Images can have multiple dimensions. Still sequential, right? You still have to have your pixels in a certain order. But now you have what are referred to as the edges to deal with. And say, well, wait a minute. Yes, there's a sequence this way, but there's a sequence this way too. So if I have a piece of data, a pixel in the center, well, I got other pieces of data, other pixels around those edges, right? So feel free to go and look it up in Wikipedia and you'll get the nerd explanation. But when you think about these, I want you to think about those in that scenario, because it's all sequencing. But is it single dimensional or multi-dimensional sequencing? Right? So here's the trick to this, guys. Remember that at this point, we're still kind of using this as a really good toy model that we're getting a lot of power from, but we're not using a framework just yet. So I don't know if it's possible for ChatGPT to work out this this simple of a model and be able to um, show us an RNN example, right? So let's find out. We're going to go back here. If you remember, this is the same prompt we had before. And we are going to go ahead and we are going to say, hey, can you modify this and show us an RNN example, right? And I think we can basically keep the same code. We made our own modifications, but I think we can generally keep the same code and we'll just start a new file. And actually, maybe I need to make that a little bigger. Let me see. Let me know if that's big enough on the screen for you guys to see, okay? So again, we're going to ask to do it only with Python code, right? No frameworks. Just show me the raw code, right? I don't even know if it's possible, but we'll see. And by the way, just as a reminder, we're using ChatGPT 03. That's a little bit of a departure for us. If you've attended my Sunday series before, you guys know that I'm a big fan of 4.0 for coding. 4.0 served us really well for multiple series, right? But we have made the switch to 03, and so far it's done a pretty good job. But just quickly pointing that out for you guys, because I know I've stated how much I believe in 4.0 previously. All right, so it's giving us the code. It's still going to be using an XOR demo. Okay, no, it's gonna be changing it up a little bit. You know what? Let me copy this over into VS Code, and that way we can all take a look at it in a little bit of a better way. Oh no. All right. So a little bit of a bigger code file. Is this going to be more of a script? Okay, I mean, I guess that's not terrible. All right, let me take a quick look at this, guys. So that's going to be our text. It's going to do it with text. Which I guess makes sense. let's see what this code runs with. I don't know how excited I am about this code, guys. I don't know if I'm excited about this. I was hoping that it would still keep the XOR example. And we actually got an error. Okay. What was that? Line 90? That is not good. Um, let's go back to ChatGPT, guys. And by the way, just as I was talking about how great O3 is, it gave us an error, right? I mean, we're gonna have to go back and look at that code because that is that's a little discouraging that that would give us an error right on the first run. I'm trying to still figure out where the T came from. The T is in reverse range of the inputs. Wait, where is reversed? Reversed is one of the native functions, right? That doesn't make sense. Does that make sense? For the range of the length of inputs, give me the reverse of that. Okay. Returns a reverse iterator on the values of the given sequence. But doesn't this resolve to an integer? Am I seeing, guys, let me know in the chat. Am I reading that wrong? I think our problems lie here, right? Because we know that it fails. It fails here because it's telling us it can't find row T, right? But here, am I reading that right? Doesn't that return an integer? But how can you reverse an integer? What do you guys think? Am I seeing that right? Let me know. So let me go back to ChatGPT. Okay, so this time it can't. It is going to go ahead and use an XOR. So if you guys don't mind, I'd rather try this one. And we'll just call this NN3 because I kind of want to take a look at NN2, if only just to see if there's a legitimate error made by O3. Okay. So here we go. All right, guys. So this looks a little bit more reasonable. So let's step through this real quick. Ayush says, can't see the whole code. Ayush, thanks for joining us over on Instagram. Feel free to come over to YouTube where you can see it in widescreen, okay? Instagram just doesn't show the widescreen. Fabrizio is doing the, yeah, I get why you need to do that, Fabrizio, but how are you reversing an integer though? That doesn't make sense to me. All right, but let's focus on this example here. So there's a couple of different things that we should already be recognizing, right? We should already be recognizing the sigmoid function, which is something that we saw in our previous examples. We should be noticing this, right? This is the same XOR table that we were learning on in our previous one, right? Here is the hyperparameters. So that's going to be 3 nodes in our hidden layer, a learning rate of 0.4 and 10,000 epochs, which seems like pretty normal hyperparameters to start with, at least reasonable hyperparameters to start with, right? Down here, we're going to have our training loop, which is basically running through our epochs, right? And then here, we are doing our backwards propagation, right? We know that by the, right, here's the backwards propagation. And then here is where we're taking the sequencing into account, right? The RNN function of our neural network. So this is basically kind of where this code is what didn't exist in our previous example. Our previous example was not an RNN network, whereas this one is. So this is where kind of like that magic happens, right? All right. So I want to do something very, very quickly. And again, I'm asking you guys to think about this in terms of our data science knowledge, right? So let's go back here. We know that this was 200. We know that this was 0.5. And we know that this was 60,000. Okay. And just to prove that out, let me go run this. All right. So remember that this is the neural network that we were running to get some really good results using our previous non-RNN approach, right? So here we were getting a pretty good loss. We got down to 3 zeros, I believe. And we got down to some pretty good accuracy numbers for all 4 of the classes, right? We're going to 60,000 epochs. So you can see here that it's not fast. It's also not fast because we have 200 200 nodes in our hidden layer, right? So that's a lot of calculations, right? So really good loss, really good accuracy, not a lot of speed, right? And it's also going to be a larger neural network because we're doing more calculations. There's more weights to keep track of, right? You can see here we now have to keep track of all these weights, right? These were our starting weights, right? That's a lot of weights that we want to keep track of, right? A lot of weights that are changing during every pass, right? So now here we're done. Very, very low loss. Very, very reasonable answers for all of the input classes, right? So we can get there with this neural network. Now, knowing what we know about RNNs and knowing that we're going to try this example, in the chat, give me your hypothesis. What are you expecting the results of this experiment to be? Are we going to have more nodes or less nodes? Are we going to have a higher learning rate or a lower learning rate? Is it going to take us more epochs to get there or fewer epochs to get there? Let me know in the chat. Remember, this is us putting all the elements together. This is us using our critical thinking skills as data scientists, right? It's totally okay to go into these experiments and think about, well, what am I expecting here? Why am I doing this step? And then when you finish, did this experiment meet my expectations? Sometimes it does, sometimes it doesn't, right? Okay, so Yassine is saying, I think better results with less epochs. Yep. That's a reasonable conclusion. Fabrizio says, fewer epochs, less nodes to get there. The RNN architecture helps capture better patterns. Yep. Yeah. Yeah, I agree with that, right? So less epochs means less training time. Because remember, epochs don't affect our runtime, right? But it does affect our training time. And then less nodes, yeah, that's a reasonable expectation. And that does affect our footprint, right? The number of weights we need to track. And it also affects our runtime, right? So yeah, perfectly reasonable expectations. So let's run it. So this is NN3. Now we're going to start with these hyperparameters, which are reasonable starting points, maybe not great values, or at least, we don't think they're great values, but there's nothing wrong with starting here. So let's go and run NN3. Okay. So we only ran 10,000 epochs, very small neural network. And we got answers almost instantly, right? What do you guys think? What do you guys think of these results? Uh, is it Ali? I think I see Ali over on Instagram. If you want a different name, let me know. But Ali, thanks for being here. I think it's your first time. Ali says less nodes. Yeah, perfectly reasonable to think that we're going to have less nodes, right? Perfectly reasonable. But what do you guys think about these results that are up on the screen now? What do you guys think? Let me know what you guys think. Let me know in the chat. What are these results telling you? So I'm seeing a loss of 0.12, and you can see the results for each class there. What do you guys think? Fabrizio says the O1 and 10 with different probabilities is not good, but the fact that the loss starts with 0.19 with just 2,000 epochs is good. O1 and 10 with different probabilities. Oh. Okay, yeah, Fabrizio says 00 and 11. Yeah, 00 and 11 is probably not great, right? So Fabrizio's talking about this one down here and this one down here. They both should result in 0. So those are off, right? They are, as you said earlier from Ali. Yeah, that's right. So it's not great, but for a first pass, it's not terrible. And it's not terrible given the size of what we're working with, right? Because Fabrizio says with just 2,000 epochs is good. Well, actually, it was 10,000 epochs, Fabrizio. But yeah, but with the number of epochs, it's actually pretty good, right? Yassine says generally good, even if it's not very sure for the first case. It can confidently identify second class, generally better than the other architecture. In some epochs, we can easily define decision bounds. Yeah, yeah. Yeah, it's not a finished state, but it's not terrible, right? What if? Well, There's a lot of things we could change here, right? We could change the hidden layers, the size of the hidden layer, the learning rate, and the epoch. So let's be smart about this, right? What do you guys think, given all that we know, what is the most effective experiment we could try next? Because remember, we're experimenting, right? We're in the lab right now. This is the thick of things. We are doing the data science work. What do you think is the most reasonable item to change here? What do you guys think? All right, guys, I'm out of coffee. So either one of you needs to order me coffee and have coffee show up here, or two, we're going to finish earlier. um, where did RNN retain the data again? It's down here in the code. It's basically down here, starting at line 64. We know that we're starting back propagation here. And then here is where it's tracking the sequence of the inputs. Yassine says, can we show the results back? Okay, sure. So those are your results, Yassine. The loss is not terrible, right? Fabrizio says, change layers to get deeper learning. One layer just gives you global patterns, also number of epochs. Hold on a second there, Fabrizio. Hold on a second. There's a big, big difference between adding layers versus adding epochs, right? Completely different implications of both of those. So we can't just, try both of them just randomly, right? We got to be smart about this. So guys, I mean, look, let's take another look at the code here. Look at this learning rate. What did we say about learning rate? More high, more better, or more low, more better? Right? Okay, so Yassine says loss is not terrible, but not improving over time. So number of epochs might not be the best choice. Adding nodes can affect runtime and training time, by the way. So learning rate is the best one. Yeah, I think the learning rate, right? What happens if we were to make that like 0.05, right? Because, I think it was Yassine that said it, or somebody said it last time, where, the analogy they used was if you were guiding someone like on a map, you were telling them like, where to turn and all that. You want them to take small steps, not big steps, right? Because if they take too big of steps, they're going to miss turns. Oh, no, go back. You should have turned right. You should have turned. But if they take small steps, it's really easy to guide somebody, right? Almost impossible to miss a turn if they're taking small steps, right? So, excuse me, why not the learning rate? That's the quickest hyperparameter, the quickest experiment we could run right now, right? Michael, hidden layers, I think. Michael, but hidden layers come with a cost, right? Why add more computational costs when we can just adjust the learning rate, right? Fabrizio says, oh, that learning rate is awful. Yeah, it's not a great learning rate, right? So let's try 0.5. Did I save that? I think I did. Sure, I did. Okay. What do you guys think? The loss didn't really improve, did it? So what are we seeing here? Anybody take a guess at what we're seeing here? Navin, nice to see you again. How are you? Loss didn't really get lower with more epochs. Yeah. Let's change those epochs. Let's go to 20,000. We'll double it. Not great, right? As you seen posted earlier or observed earlier, this hasn't really changed a lot, right? The loss kind of sort of stayed the same, right? Yeah, for BTO size, it's not learning. Yeah. So now that we've done other things, we've explored other options. Yeah. Now I think it's completely okay to say, hey, wait a minute. Let's 5x our nodes. Are we any better here? Did anybody else notice something? Did that run faster or run slower? Michael says not much difference. Yeah, that's right. Stuck in a local minima? Maybe. Maybe. Let's make it a little bigger. What if we 10x the number of nodes that we started with? Oh, excuse me. Is anybody happy with this performance? Now remember, we're also doing back propagation with this RNN, right? So that means we've essentially increased the number of calculations that we're having to do, right? So was anybody happy with that performance just now? That was terrible, right? Took a long time to get there. All right. So Fabrizio is saying change initial seed weights, maybe? Maybe. So remember how we talked about experimentation, right? Part of experimentation is knowing what to adjust and kind of have like some sort of target of what you're aiming for, right? So, can't we do that? In proper data science terms, don't we have a baseline to work against? We do, right? Because guess what? We have a model that we know works, right? Um, we know that these hyperparameters work on the same data, right? The same XOR table. So is it reasonable for us to be able to use this, at least as an initial guideline? And I think it is, right? So what happens if we come over here and we say the hidden size is going to be 200 and the epochs are going to be 60,000? So we're going to closely mimic over here, right? What happens if we run this? Let's let that go. So Fabrizio says, I think the problem is how the features are being injected. Can we visualize data, do some EDA? There's 4 rows, Fabrizio, right? We can't lose sight of that. It's a toy example with an XOR table. Can't really do EDA on 4 items. And remember that we already have a model that works. We're just trying to see if this is a better way to go about it. Right? Because that's part of the experimentation process. Just because you find a model that works doesn't mean you stop. You keep going. And that's part of the champion model process. And that's essentially what I'm starting to show you guys here. Right? You have a baseline and you're trying to beat that baseline. We have a model that works. It's just a very simple model. Salient says, is it because of the activation function being 10H? Maybe. But I think it's more about the number of calculations that we're doing. Because remember, before we were in what's known as a feed-forward neural network. It just goes through once, finds the weights, and you're done. But now that we've introduced the RNN portion of it, you're also introducing the backpropagation. So now you're going through the network, but then you're also going backwards and saying, oh, wait a minute, let me adjust this, this, and this, and this, and then you're going through it again, right? So I don't think it's the individual activation functions. I think it's just that we're doing a lot more calculations. And we can see that here, right? Because look, now we've gone up to 200 hidden nodes, 200 nodes in our hidden layer. And look how long it's taking just to get to that first epoch result. So this raises an interesting question while we're waiting for this, right? We're using different hyperparameters, completely valid. We're potentially going to get similar results to the ones we got before. And let's assume we even get better results than we got before from our baseline, right? Our simple feed-forward model. Have we won? Yassine says, are you sure your Mac is okay? Yeah, well, you got to ask that question, right? Like, have you won? Like, maybe this does get to a better model. Like, you can say that quantitatively. Oh, look, the loss is better. The classification is better. But have you won if the model is slower? Maybe, maybe not, right? Yassine says it's fighting for its life. You know what, Yassine? I am due for a new Mac. I run everything on a Mac Mini. I love the Mac Mini platform. That's just me. But I am overdue for a new Mac Mini. I want to get one of those. I've been pricing some out, and I don't know. We'll see if that's in my budget for this year. But I'd love to get a new Mac Mini. But I mean, look how slow it is, guys. And we're going to 60,000 epochs here. So let's assume we're going to get to a better model. But if the performance stinks, have you won? Yassine says absolutely not winning. Yeah. I mean, this performance stinks right now, right? So I hope you guys can see that, fancier is not better. Sometimes a simple model gets you to a better answer, right? And maybe we can say, hey, look, maybe RNN isn't the best solution here. Is it feed forward? Maybe, but we have to try other experiments. So far, it's the champion model, but maybe we want to try CNN next, right? But this performance right now is terrible. In a way, it makes sense, though, because remember, if we're going from just doing the forward propagation to doing the forward and backwards propagation, we've massively increased the number of calculations we're doing, right? So maybe the win is in just doing that forward pass. Maybe you don't need back propagation. I mean, look at that. Our second result of epochs came up. And we sat here and we waited for an additional 2,000 epochs, and we gained 0.0002 in our loss. That's a slow day, guys. That's a slow walk. So we have to think about that, right? Just because you run an experiment doesn't mean, or just because you're running what you think should be the latest and greatest experiment, latest and greatest architecture, doesn't mean it's always going to have a positive result. Something to think about, guys. All right, anybody have any additional thoughts while we're waiting? I think we're going to be waiting a while, guys. Jeez, this is slow. This is slow. And we went to 60,000 epochs. Good lordy. I'm looking here. 1253, 1252, 1254, 1259, 12.7. So we're getting slightly better loss. We got a better loss here. But this is not good, guys. Should our experiment be based on looking for optimal solutions? So starting from the minimum resource consuming hyperparameters, and then increase based on that while choosing the one with less impact on resources. Hard to say, Yassine. Hard to say. You can choose whatever you'd like. You know, there's no laws to it. But in my experience, the biggest determinant of what you need is going to be like the due date, right? Because remember, in everything we've talked about, this experimentation, the hyperparameters, the number of calculations we're doing, we've completely ignored the element of deadlines and time, right? There's going to be times when you have to ship a model that you wish you had more time to work on, but you have to ship it because the project manager said so. Like, that's just a real world reality, right? So keep that in mind. Yes, I mean, that's how I would answer you. See, there's many ways to go about it. Just pick one. But most of the time, it'll just be time. Salient says, better architecture comes at computational cost. You know, that sounds suspiciously like, what is that called? An oxymoron, right? Is it better if you have a more computational cost? Like, is it better? You know, like I said, have we won here? I don't think we've won, right? So that's better in quotation marks. This doesn't feel any better, right? So yeah, Salen, I'd say that you're posing an oxymoron there, right? Sure doesn't feel like we're doing any better. Man, this is going to take a while. And we're basically at the same loss as before. So this is also a good time to kind of illustrate what I mentioned to you guys about early stopping, right? If we know that we can get to a model that gets us to this loss, why would you accept this loss at 6,000 epochs? Like, yes, maybe that could improve, but if that's going to take you another 3 hours to get there, I could run a lot of experiments in 3 hours, right? So this is where you might say, okay, you know what? Let's stop this. Let's move on to something else. Let's stop here. We've reached the best we can do with RNNs. Let's try CNNs. Like, that would be a valid conclusion at this point, right? We would exercise our early stopping decisions and We keep the results, right? Because we want to document all experiments, but we move on to something else. This is a really good example of that. We're at 8,000 epochs, and granted, that is the lowest loss we've seen so far, right? We've never hit 1251. So kind of sort of headed in a good direction, but not very fast, right? So something to think about there too, guys. All right, so we covered a lot of ground today, guys. I hope that this has been beneficial in understanding all of the different approaches that we could be possibly using, right? Because there's a lot to it, right? There's a lot of different variations, a lot of different things that can be tried, right? Yeah. So I'm going to let this run in the background, see where it ends up. But I think I want to wrap up here because we've gone for almost 3 hours. But I want you guys to think about all the different things that we've covered today, because that means that next week's lightning round review is going to be very interesting, right? Lots of things to talk about in the review. Feel free to look up the definitions for CNNs and RNNs in the nerd explanations. But the bottom line is that sequence matters. We're going to see that in NLP. You're going to see that in image processing, right? But sequence does matter. Maybe it didn't matter for us in this example because the XOR table is only 4 inputs, right? Four rows. 4 rows, 2 different classes, right? But you can kind of get a feel for how you experiment your way to a solution, right? Let me know if you have questions in the meantime. But really happy you guys attended. Hopefully you guys get something out of this session. We're also going to be gravitating more towards using some frameworks because we haven't looked at frameworks yet, right? So next week, I promise that we're going to do at least one of these examples with a framework. It's time that we do that, right? It's time for us to leave the raw code and go to the frameworks. And who knows, maybe we'll see better performance, right? In theory, the framework should help you see better performance. So guys, thank you so much. Really appreciate all the participation. Really happy to be spending Sunday with you. In the chats, there is a link to sign up for my data science school. Guys, I'm trying to get to 1,000 signups prior to opening. At this point, it's in danger of me having to kill the project because I'm not seeing the number of signups I'd like to see to have the school be self-sustaining. But if you haven't signed up, please sign up for my data science school. I want to open it by August 1st, but I'll never get to an opening phase if I don't get enough signups, okay? So thanks for being here. Thanks for all the feedback. As always, we live in a very dynamic world. I worry about all of you. So please, take care of yourselves, take care of your families, and I'll see you guys next time.